Hello everyone. So in the previous video, we have looked a little bit on central limit theorem. And in this video, we're going to look at confidence interval. All right. So these two are actually really much closely related. And in fact, I would say that this topic is pretty important because you can see that later on when you have mastered confidence intervals and you are going to go on to the next topic on significance testing, or what we call as hypothesis testing, and therefore it is important for you to actually really know about these concepts and grasp the foundation of what this is about, because you're going to use some of these steps that you have in confidence interval in the next topic later. So if you, by now you would have seen a lot of Zach formula, right? So how Zach formula is used for normal distribution, and you can see that we can actually use this Zach formula for the purpose of inferring parameters of population. For example, it's quite difficult for us to calculate the whole population mean, right? But it's quite simple if we take like a random sample and calculate the mean and all that. And so basically, generally confidence interval, this theory allows you taking values from the sample, and we actually give it an upper bound and lower bound where most of these sample values will lie. All right, and we actually call this the confidence interval. But so in this video, basically, we'll basically start with the concept of confidence interval. All right, which I think I'll probably best explain it in with an example. All right, and then after that, we'll look at the formula for it and how we're going to apply it. And then from this formula also, you can see that there are like a few different types of it. When you know, there are cases when in the situation or in the question that the sigma is known, and there's also a situation when your sigma is unknown. Yeah, so let's look at first the concept. All right, so let me just give you an example. All right, say we actually have a company that produces light bulbs. All right, and then what this company wants to do is that it wants to estimate the lifetime of your light bulbs. So how do they do this? All right, so it can't be that they take the whole population or whole stock of their light bulbs. So what they do is that they actually take random samples. All right, let's say that these random samples, they take random samples of 60 light bulbs. All right, and what they do is that they test them continuously. Basically just run it over and test it out continuously until it burns out. All right, that's basically how you actually look at the lifetime of a light bulb. Okay, and it is known that the standard deviation of the population is actually 140 hours. All right, so after looking at the experiment, after testing out all these random samples of 60 light bulbs, it was found that in these samples produce a mean lifetime of 1456 hours. All right, so again, remember from what we learned earlier, we're taking random samples of 60, right? So the mean for these samples is then being denoted by which symbol here? I'm going to give you 2 to 3 seconds to really think about it. Will it be a mu or will it be an x bar? All right, so, and if you have guessed this one, then you're right. All right, so always remember that mu actually applies, both symbols mean the same, it's average or the mean, but then for mu actually indicates population mean, while x bar here actually indicates sample. So this 1456 is the data that we get from the random samples of 60 light bulbs. All right, so what do we know about this confidence level again? So say you want to, we have tested 60 random samples, right? and we have mean of 1456. Chances are if we take another random sample of 60 light bulbs, we definitely would not get 1456 hours as the average. We could probably get 1455, 1457, and so on. All right. But what does this tell us? This mean samples of X bar of 1456 here, this can be used to give a point estimate. All right. And we call this the point estimate of a population mean mu. All right. So basically, what's a point estimate? It just estimates a population parameter, because we're taking this and we base this as a sample to actually infer a parameter, which is the average lifetime of your light bulb for the population. So what do we know about confidence level here? So basically, this being our point estimate, which is my X bar here, my sample means. All right. So therefore, we can't just basically say that average lifetime for the bulb is 1456. And usually it's better that using the central limit theorem, we actually use the interval estimate. All right. And this interval estimate basically just gives an upper bound and a lower bound. Basically, it gives you one sort of like an interval. All right. And this is what we know as, this whole thing here is what we know as the confidence interval. All right. But this is being the point estimate. And what do we call this? And usually this part here, this lower range here, is what we call as the lower confidence limit. And this is the upper confidence limit. And see to that the distance between these two is actually the same. And basically, we also call this interval here, right? This interval between here. There's another term for it, just for you to know. And we call this the margin error. All right? So that's what it is about in general. So that's first on our concept. All right. So now we're going to move on to the formula to it. So basically, instead of just a point, we use a point estimate, and then we actually allocate a lower confidence limit and upper confidence limit, and that will actually form our confidence interval. And besides confidence interval, you will see that in questions, sometimes they actually also mention confidence level. All right. So basically, confidence level is just the percentage of your confidence interval. All right. So just in case you're wondering, like, okay, what does this mean, right? So basically, it means if we are, let's say we are talking about confidence level of 95%, all right? So it means that if we select 100 samples, so there will be 95 samples that will actually, when we test out, will have the mu of what we have claimed it to be, all right? So if you remember what you have seen earlier, this confidence interval, right, with the point estimate. So it goes by, let's go with the how now. How do we solve questions and the important formula for this? So it is actually given by your X bar minus Z alpha of sigma over square root of n. So it's actually falling in between these ranges here. So I'm just writing this down. And as long as you can remember the first term, you can remember the second term. It's basically a minus and a plus. All right. This is your Z alpha of sigma over square root of n. All right. So this is the general confidence interval formula for population mean. Okay. And this being the mu, and then this is actually indicating, as you can guess it, right? This is the UCL, and this is the LCL, the lower confidence limit, and this is the UCL. All right. So now, how do we actually write it, right? So confidence interval is written as basically, you have this form. It's actually in a form of, the general formula for it is actually just in the form of square bracket. Do you notice what's happening here? It's basically just me writing down the first term over here, right? This first term here is actually on here, and this term then will actually be here, and it's actually an x bar plus z a alpha of sigma over square root of n and a close bracket. So that's how we generally indicate this. We're going to look at more, and as you can see, all these terms are pretty familiar to you. I'm going to show you what this alpha basically is later. You will see this later on in your significance testing in the next topic as well. All right, so let's move back on to what the example was earlier. Remember, if we go back to the earlier example, so now we're going to start with an example here. If you go back to the example earlier, we have talked about the population mean. So I'm going to write it as mu of 1456, right? So say we have a population mean of 1456 for the average lifetime of the bulb, yeah? And then after that, what else? And if I just try to recall back about what we talked about earlier, we actually have the random sample. Okay, and then we have the standard deviation of 140 hours, and then the random sample is 60 sample earlier, remember? All right, so let's test it out with 95% confidence interval. All right, so you want to get a 95% confidence interval for these light bulbs that we talked about earlier. Okay, so now first, you already know all these data here, and if you can guess it correctly, the type of distribution that you will be using. All right, so remember in the second topic, we have learned about normal distribution, binomial and Poisson distribution, and you have guessed it correctly. Remember, things that are related to population usually will go back to the normal distribution. All right, so of course, remember it's always a range because we're talking about 95% confidence interval. If you I'm just redrawing what the normal distribution looks like. This is my mean here, which is 1456. All right, we're talking about range, isn't it? So therefore it will be what we call this side here. All right, so it will look like this, where this region over here will be 95%. All right, which means we actually want to find this LCL here and my UCL here. So everyone can pretty much agree to it. So if this is 95% confidence interval, so note that this then becomes the remaining 5%, right? So which means this will be 2.5% and this will be 2.5%. So when you have a two-ended range like this is something that you want to take note on, all right? And this 2.5% here is being translated into 0.025, and this itself is actually my alpha. All right, if you remember from what we saw earlier here, all right, this is my confidence interval formula. And just in case you're wondering about this alpha here, right? So this is actually the alpha here. All right, so which means if I am going to write it back to whatever it is, okay, so it means that I am going to write my confidence interval in this form. I'm going to have x bar minus z of my 0.025. all right, and then this would be sigma of over square root of n, and then another would be x bar plus z of 0.025 sigma over square root of n. all right, so note that we have written down this. Then it's time for us to get what it is, right? So again, because we are inferring that the population mean is 1456, and in which we actually take the samples of it, 60 of them, all right? So I will still take this as my 1456, which is given earlier. All right, how do I find the z of 0.025? So this works slightly differently from whatever that we have looked earlier. Remember in the previous topics and all that, if you still remember what your z is, yeah, do you? So your z is actually the z table. Remember the z formula, where in this case it will be x bar minus mu over sigma over square root of n. All right, because in this case we're talking about samples. So what you did earlier when you actually look at, or when you learned normal distribution, is that for the z, you basically just look at the z value, which is the probability of, and you find the probability of the z value after you have got that. Now this works slightly differently. Over here, we already have the probability, all right? And now you want to find the z value. And that is why you actually need to find from the normal table, the z table, in a reverse way, all right? Which means what you do is that you work it out differently. When before this you're looking at the z value, and then you look for the probability. Now you already have the probability of 0.025, all right? So what I would like you to do now is to take out your z table and then look out for 0.025, all right? And then when you look at 0.025, which means that this is the probability of 0.025, and when you refer to the z table, you will you will sort of get this value, which is 1.96. all right, and then once you have known this, so be very careful with z 0.025, right? Even though you know that it's 95% significance confidence level earlier, since it's normal distribution, the 5% is then divided into 2, because you want to take note on the 2 range at the end, on the left hand side and the right hand side. So once you have got this, all right, standard deviation earlier is actually 140, right? And then your n is 60, right? I'm just going to put the plus here. So this is actually what I call the lower lower confidence level, all right? And we, as long as we already have this value, we repeat the same, right? Don't have much space here, so I'm just going to rewrite this in this way here. You can see it's exactly the same, only that you are adding up the value, all right? So that's the main point here, and you will get that. So do calculate what you have here, and you should be getting somewhere around 1420.58, comma 1491.42. If you calculated and if you have calculated and you get slightly different value from these values here, it's fine, because of just the decimal point difference, all right? So from here, we have actually looked at an example. Remember earlier when I mentioned that we have looked at the concept, and then we have looked at the formula. In fact, if you look at the question earlier, do they give us the sigma, which is the standard deviation. They do, right? So that is actually the case where your sigma is known. All right. So I just want you to be clear that we have actually looked at this part here. And now that you're familiar with this, so pretty much if you look at it, it's pretty much simple, isn't it? So you just need to know the confidence interval formula and then just apply it accordingly. All right. So now we are going to look at when sigma is unknown. All right. What do you do when sigma is unknown? So if I just summarize it, right? Earlier when your sigma is known, right? And then you actually have it as, your confidence interval is written as x bar minus z of alpha, sigma over square root of n, x bar plus z of alpha, sigma over square root of n. All right, just a minus and a plus over here. What about when it is unknown? All right, so this is for the known. When your sigma or your standard deviation is unknown, all right. So usually when it is unknown, it's some point that we actually estimate the standard deviation. All right. When sigma is unknown, we actually use this thing called the t. So over here, we actually use the z, right? The z table. So when sigma is unknown, we actually use the t distribution. All right. And from the formula, you will see that it's actually just the same. So how we represent it would be t equals to x bar minus mu over s over square root of n. All right, with n minus 1 degree of freedom. All right, that's just the representation of what it is for t distribution. And instead of your z table, which is this formula that you see over here that you use when sigma is known, when it is unknown, you just use this one here. All right, and in fact, if I'm going to write it down to the general form of my CI, you will see this is x bar minus t of s over n. Of course, I have an alpha here as well, and this x bar plus t s over square root of n. And if you just compare these two formulas here, right? If you compare this formula and this formula, basically you can see that, okay, everything is exactly the same, only that when sigma is unknown, this is when sigma is known, and when sigma is unknown, we basically do not want to, this is still the standard deviation, but we do not want to just confuse, we just want to be very differentiative with the symbol here, and therefore we actually indicate it as S. And of course, we actually have a T table, all right? So T table is exactly like your Z table. This is still the same way of you doing what it is and all that, all right? And of course, when you have this, sometimes, remember we talk about estimating the variance, all right, when your sigma is unknown, right, and you need to get your S standard deviation. Also, when you square your standard deviation, you get your variance, right? So for your variance, S square n, all right, is given by this formula here, which is 1 over n minus 1 square root of your xi minus your x bar n square. You would have been very familiar with this term because of from where you learned statistics in your school last time, all right? But this is just basically for you to just refresh on what you can get. So once you have got your variance, you'll be able to get your S. And sometimes in the question itself, they might already have given you, so you just need to replace this in, all right? And so just in case, how do we decide, right? Please note that sometimes in some other references or whatever, you might see that even though when sigma is unknown, All right, and then they mention about the standard deviation. You will be seeing that sometimes in certain examples or certain books, you can see that they actually use this exact table formula. And in fact, you can see that these formula are exactly the same, and the only difference is the ZA and the TA. All right, so what happens is that, you know, for normal distribution, we actually go by the criterion of your N of large sample, right? And your N is actually, if I'm just going to write it here, your N is basically more than 30. That's your sample size. So what happens is that when you actually use Z table in comparison to T table, when sigma is unknown, when we actually have N more than 30, which is large sample, you can see that the difference is basically very, very minimal. All right, that's why in some texts you will be seeing that some still use Z table. So basically, rule of thumb is usually when your sigma is unknown and the sample size is small, all right, you actually use your T table here, which is this formula over here. Okay, but don't get confused if you see that sigma is unknown and you still see some references or some books using the Z table, because the difference is actually very minimal. But just know that in this course here, we actually deal with this for sigma known for this formula, and when sigma is unknown, we use the T formula here. All right.